All right, here's problem 27. I'm afraid you're going to learn something on problem 27, and that's not necessarily what you're looking for in an exam situation. This is a practice final exam though, so I suppose it's all fair. And the reason I say that is because typically the elementary statistics text, at least the few that I'm familiar with, they teach one sample hypothesis tests in a very restricted manner. And they do so to keep you away from some subtleties that can show up when, after all, when you're first exposed to it, you don't need subtleties. You've got to find your way through this complicated procedure. But the subtleties arise, believe it or not, out of whether or not your test is two-tailed or one-tailed. If you're creating an experiment, how you ask the question will determine if it's two-tailed or one-tailed. If you're taking an exam and working on problems, the manner in which that problem is stated determines whether it's two-tailed or one-tailed. It's maybe worthwhile to give an example here, because one-tailed and two-tailed tests are real. If, for instance, you are manufacturing stainless steel ball bearings with an intended diameter of 1/2 inch, you could ask, depending on the type of machine you're using, two different questions. If you're using a machine that could conceivably cut that ball bearing with too large a diameter or too small, you might set up a tolerance around this 1/2 inch of 0.01 inches, so that an acceptable ball bearing would fall for you between 0.49 and 0.51. If you then wanted to test whether or not that machine was working, you would consider an extreme result to be something outside of either too large or too big. And then you can see that there are two regions of interest, one too big, one too large. The null hypothesis is always going to be that the population parameter is equal to some value. Yeah, you want the population parameter, the mean diameter of those ball bearings, to be equal to 0.5, and you're going to set some value on either side of 0.5 as significantly different. Over here, if you have a machine that cannot physically cut the ball bearing smaller than 0.5, then you're interested in seeing that your machine is cutting ball bearings from 0.5 to 0.0 to 0.51. Yeah, and so significantly different for you would mean significantly larger, one-tailed test. So they're real. And I think you've seen, and I think you probably understand, that if you do a two-tailed test versus a one-tailed test, here's a one-tailed test, here's a two-tailed test, and you pick yourself some value of the level of significance, alpha is the level of significance. It's the region in these distributions in which you could be making a type 1 error. In the two-tailed test, you distribute that probability in two regions, right? This is alpha over 2, this is alpha over 2. In a one-tailed test, you distribute it in one region. So understand that these shaded regions have the same overall area. You've just put all that area out in one tail in one case, and you've divided it in two and put half the area in one side, half the area on the other side. The area is equal to alpha, okay? So now let's go to your problem. Because like I said, there's a subtlety here that you're probably not aware of. I'm going to draw two more, because I'm going to switch from talking about alpha to talking about p-values. So the manner in which you calculate a p-value in a two-tailed test and a one-tailed test is actually different. Right? If you have a test statistic And we're going to use a situation in which the test statistic is the same for both two-tail and one-tail test. This is a test stat. Whatever that value is, and whether it's a mean or a proportion or whatever statistic, the p-value is the probability of obtaining a result as extreme or more extreme than the test statistic. Yeah? So in a two-tailed test, separate these two, the manner in which you calculate it is you find this area. Yeah? And for a two-tailed test, the p-value is equal to this area times 2. You probably don't recognize that because your calculator is doing that for you. Yeah, when you run a hypothesis test with your calculator, there's a place to enter whether mu is not equal to mu0, greater than mu0, less than mu0. Those last two cases are one-tailed tests. The first case, mu is not equal to mu0, or p is not equal to p0, those are the two-tailed tests. And if you experiment with that, you'll find the p-value that you obtain when you pick a two-tailed test is twice that when you pick a one-tailed test. Okay? So that's very different than this case, where the p-value is just equal to the area. Okay, I'm ready to do your problem now. You may not have recognized that before. You just have to go back to the definition of the p-value. The p-value is the probability of getting a result as extreme as the test statistic or more extreme. So the test statistic in two-tails could have fallen over here, or it could have fallen over this. Well, you double it. So let me read the problem. An experimenter conducted a two-tailed hypothesis test on a set of data and obtained a p-value of 0.44. If the experimenter had conducted a one-tailed test on the same set of data, which of the following is true of the possible p-values? So I'm saying that an experiment conducted a two-tailed test, he got a p-value of 0.44. Yeah? That means that this area plus this area is 0.44. Okay? So this area and this area totals 0.44. So in the case of the one tail, right? Instead of twice that area, it's just equal to that area. The possible p-value is over here. One of the possible p-values is over here, and it's 0.22. Here's the last subtlety for this problem. If you're conducting a right-tail test, this p-value in this equivalent one-tailed experiment is 0.22. If, however, you're conducting a left-tailed test, then you're going to take this area, which is 0.78, as your p-value. Yeah, and there's the answer to that problem. Like I said, real subtleties. Talk to you later.